we can go ahead. Oh. Okay, well, it's our pleasure to have David Stapleton here today from UC San Diego to tell us about studying Fano hypersurfaces with holomorphic forms.
All right, thanks, Laura, and thanks to the organizers for inviting me. I understand that although it's the Derived seminar, there's some freedom, and thank you for accepting me into your derived world. Okay, so yeah, I wanted to talk about studying Fano hypersurfaces using holomorphic forms, or maybe more generally, Fano varieties in general. And the title is a bit contradictory, of course, because if we start with a smooth projective, complex, rationally connected variety, it's X, then X never has any holomorphic forms. So the Q forms, which is global sections of omega Q of X, automatically vanish. Can you hear me okay? Okay. Right, and from an algebraic geometry perspective, this is a bit unfortunate when you're trying to sort of restrict the geometry of these Fano varieties. So, okay, your Hodge diamond looks something like this. And I guess one of the points is that the outside groups in your Hodge diamond, these are birational invariants of your variety. So outside groups are the birational invariant Hodge groups. And so for these Fano manifolds, we never have these holomorphic forms, so we don't have access to this great tool for studying varieties. So Fano manifolds never admit holomorphic forms in characteristic 0. This is sad. But if we go to characteristic P, Kollár has a nice idea. So Kollár notices in characteristic P, they can. So Fano varieties in characteristic P can have holomorphic forms, and his idea is to look at p-cyclic covers in characteristic P. So I just wanted to spend a few minutes talking about where these forms arise, because in some sense, this is sort of the surprising aspect and sort of the input to geometry that you get in characteristic P that you don't have in characteristic 0. Okay, so let me start by recalling what a cyclic cover is. So to define a cyclic cover of your variety X, you want to start with a line bundle, L over X. So I'm thinking of it as the total space of the line bundle. And you start with a section of the P tensor power of L. So let's work in characteristic P. So we have this setup. So we can define the P cyclic cover of the section as follows. So you consider the multiplication map that goes from the line bundle to the line bundle tensor P. And inside the line bundle tensor P, we have the section. So now we can just look at the pre-image inside the original line bundle. So let's call this map M for multiplication. So if we look at M inverse of S of X inside L, This is some p to 1, in this case, inseparable cover of your original thing. And we can call this our cyclic cover. Okay. Right, so sort of the cover group of this map is just the pth roots of unity, but in characteristic p. So this is some slightly fancy thing. This is a group scheme which is not reduced or whatever. But anyways, if you just think about this in characteristic 0, the cover would just be sort of p different sheets, and it would be branched along the 0 locus. So locally, we can look at the equation for y. Y has equation y to the p equals s inside L, where y is the fiber coordinate and we say that y is the branched cover with branch divisor s equals 0. Okay. So this is some natural construction you can make, and it's a very nice source of examples of varieties. In our case, these varieties these p-cyclic covers will be the sort of Fano varieties that carry these holomorphic forms. Okay, so let's assume for simplicity that y is smooth. Okay, so associated to this sort of cyclic cover, because we have this variety that lives inside the line bundle, we have these two natural sequences associated to it. So the first sequence is just the relative cotangent sequence of the line bundle, which maps to X.
Can I ask about the smoothness of this? So is it like in characteristic 0 equivalent to smoothness of the original space and the divisor you are branched at?
Right, so I guess if assuming that the branch divisor avoids maybe, I don't know, yeah. So definitely if the branch divisor is smooth and the original hypersurface is smooth, then your thing is going to be smooth. In characteristic P, it's more complicated for sure, and I'll mention that in a second. But for now, I think it's best to assume it's smooth. Right, so in characteristic P, it will be the case that these things are always sort of singular. But this is sort of a mild point, and one shouldn't really focus on this, I guess. So I'll mention that again in a second. All right. Thanks for the question. Okay, so we have these two sequences. We have the relative cotangent sequence of L to X, and we have number 2 is just the cotangent sequence for Y living inside of L. And I want to use these sequences to sort of, these are the most obvious sequences, and I want to show how you can see these holomorphic forms arising from these sequences. And I guess the most important point is that if you look at what this map is given by the derivative of y to the p minus s. But because you're working in characteristic p, this ends up just being the derivative of minus s. Okay, so what this means is that this map here factors through the pullback of forms on X. Okay. And okay, it's not maybe so obvious that this map factors, or it's not obvious that that is interesting, but it ends up being the key. So you can look at the, I don't know why I called it, oh, I guess it's a kernel of a different map. Anyway, so you can look at this this co-kernel here, which is the kernel of a map like this. And I guess if we're assuming y is smooth, then everything's sort of obviously exact. Okay, and this gives us some sheaf, which is k, and it maps into omega y. And I guess this is enough information to say it's a vector bundle, which is nice. But really, to get a form, we would like some sort of line bundle here. So the thing that's best to consider is the determinant of k. So the determinant of k is easily computed to be the pullback of omega x twisted by y, maybe restricted to y. And this is a line bundle that lives inside wedge n minus 1 of omega y. Okay. And now the point is that this thing can be can carry a lot of sections, and thus that you have a lot of n minus 1 forms. So this can admit many sections. Okay, and let's just see the output of the computation that gives you this. So if you look at this omega x twisted by y restricted to y, this is just the same as pulling back omega x twisted by L to the p. And omega y, you can also compute as just the pullback of omega x twisted by L to the p minus 1. So there's this funny difference here, and the difference makes all the difference, I guess. Okay, so when is y Fano? Y is Fano when the second thing is anti-ample. So when omega x tensor L to the p minus 1, inverse is ample. 2, y has n minus 1 forms when this thing has n minus, when this thing admits global section, when H0 of omega x tensor LP is non-zero. Okay, and the point is that these things don't have to occur at the same time. Okay. Okay, so maybe this is a little bit abstract, but let me be a bit more explicit. So if you have a degree p times e hypersurface, y prime inside Pn plus 1, so there's sort of a natural way to degenerate degree p times e hypersurfaces to p-fold cyclic covers of degree e hypersurfaces. So these specialize. Maybe it specializes to some y, which is a p to 1 cyclic cover of x, which is also a hypersurface of degree e. Okay, so what you should think of inside the projective space is that you can degenerate y prime to some non-reduced hypersurface of degree e with multiplicity p. And then the point is if you sort of let's see. So basically, if you normalize this total space, let me see. So you want to degenerate to some sort of multiplicity p hypersurface of x, and then after passing to a suitable base change, you'll be able to replace this p times multiplicity p times degree e hypersurface by this cyclic cover. And so the branch divisor in this situation is S inside H0 of OX P times E. Okay, so it's easy to sort of compute when Y will be Fano and when Y will have global sections. So if you're in the situation where P times E is less than n plus 1, then Y will be Fano. And if n plus 1 is strictly less than p plus 1 times e, then the global sections of wedge n minus 1 of omega y is non-zero. Okay. So it's not necessarily that many Fano or that many degrees of Fano varieties, but it's it's very interesting because this is something that is sort of special to characteristic P. Maybe another thing to remark is that you would essentially, a reason you would never really expect a phenomena like this in characteristic 0 is because this injection of this line bundle into wedge n minus 1, this is sort of a destabilizing subbundle, which is something which I don't know, maybe a precise reference for the fact, but in characteristic 0, you expect sort of the tangent bundle and the cotangent bundle to be stable, or at least semi-stable, especially in the canonically polarized cases. Or
what is n in this? Is a dimension of y?
N is always the dimension, yeah.
Okay, thanks.
Yeah, thanks. Okay. Yeah, and I guess the main technical problem here, which is not something big to worry about, is that y in these cases are not actually smooth. They admit some mild double point singularities. And sort of the difference between characteristic 0 and characteristic P is that in characteristic 0, you only have to check for singularities along the branch divisor, but in characteristic P, you have to check for sort of singularities everywhere. And so they could admit some mild double point singularities. But I guess one of the points is that these are not very problematic, and Kollár can resolve these singularities by some finite number of point blowups. And moreover, that these holomorphic forms extend to the resolution. So although you might be unhappy working with a singular variety in many senses, you should think of these as being Fano varieties that admit holomorphic forms. Okay. Anyways, but this is some small technical problem.
Can you please say again where are the sums of squares coming? So, like, why they're singular away from the branch locus?
Right. Okay. Yeah. So if you look at this this equation, so you still have this local equation. Let me maybe do it in here. You have y to the p minus s equals 0. So in characteristic 0, if you have an equation like this, you would look at the two derivatives, or not two derivatives, but there's n plus 1 derivatives. So there's py to the p minus 1, and there's the ds dx1 up to ds dxn. So these derivatives sort of refer to whether or not the section is a critical point, or this map is locally a critical point. And this section in characteristic 0 will say that you only have to look at the critical points that are on the branch locus, which end up just asking whether or not the branch locus is singular or not, which is, I guess, what you were asking earlier. But in characteristic P, this is not a condition. So this equals 0 automatically because it's P. So anyways, you end up with these sort of n functions, which you would expect to vanish simultaneously at a finite set of points, right? And so this vanishing is where the singularities happen. So you have generically you have finitely many singularities, but you can maybe assume that the Hessian is non-degenerate of these things, and then that's sort of what gives you these double points. So in characteristic 2, you should be a little bit more careful, but I guess most people are maybe too afraid to work in characteristic 2 anyways. So depending on who you are. It is worth pointing out that the best results in many cases occur in characteristic 2. So maybe it's not good to be afraid, but yeah, thanks for the question. All right. Okay, so now we have these forms in characteristic P, and this is sort of how they arise. And now the question is, how do you get these results in characteristic 0? And it's sort of a typical degeneration argument, which would allow you to lift these results to characteristic 0. So what you would start with is maybe a scheme, let's say YZP, which is a p-to-1 branched cyclic cover. In mixed characteristic. And sort of the prototype for an application is we need first a property. So a property that behaves well under specialization. And to use these holomorphic forms, we need also that this property is able to be controlled by holomorphic forms. So, and that can be controlled by holomorphic forms. And I think, anyways, I think it's worth thinking about which, sort of more generally, which things can be controlled like this. I think it is frequently the case that a lot of things we do in algebraic geometry are sort of controlled by holomorphic forms. And so usually this is not a very strong condition. But anyways, okay, so I want to talk about the first application. So Kollár shows the following. So let X inside Pn plus 1 C be a very general hypersurface of degree D and dimension M. So if D is at least 2 times the ceiling n plus 1 over 3, which is roughly 2/3 n plus 1, then X is not ruled. In particular, it's not rational. Okay, so you might complain a little bit that, okay, so I said that my typical application occurs when you look at cyclic covers in mixed characteristic, and I'm already not looking at cyclic covers. But anyways, you can make some degeneration of a hypersurface in characteristic 0 so that the special fiber is a cyclic cover in characteristic P, and that's the type of thing you might work with instead. Okay. So let me sort of go through how you can make an argument like this. So the first point is that the property of being ruled specializes well in families. So recall that X is ruled if X is birational to Z cross P1. Okay, so Matsuzaka proved that ruledness specializes well. Okay, so okay, this is some general statement, but maybe you could say you could try and say something precise that if you have a normal scheme, let's say a reduced irreducible central fiber, and the generic point is ruled, then the central fiber is also ruled. Maybe you should work over a spec of the DVR or something. Anyways, the property of being ruledness specializes very well. In many cases, you're allowed to work with quite bad singularities, which is extremely useful. And okay, so we have this nice specialization property, and we also need to know that it's controlled well by forms.
Can I ask, so specialization for ruledness, is it more or less the same as exceptional divisors being ruled in this case?
Yeah, so let's see. Yeah, so I guess yeah, what do I want to say? That I guess that's just something like you take the generic point, and this is birational to Z cross P1 over the generic point of Z. Yeah, so the point is that somehow you want to eventually apply a result, I believe, of maybe it's Matsuzaka, a result of Matsuzaka that says if you have a regular scheme, then any exceptional divisor over the regular scheme is ruled. And so you have to be a little bit, so it turns out you're allowed to work with schemes that are not quite regular, but basically, if you have an exceptional divisor over here, anyways, it either maps to a regular point in Z, in which case it's ruled, or it's sort of contracted by this map to Z, and then you can sort of argue that it has to map to this P1 direction, and then it's also ruled. So it's a bit subtle, but yeah, it sort of comes down to a certain application of ruledness of exceptional divisors. But there's a bit of a dimension massaging as well. Okay. Yeah, thanks for the questions. All right. Okay, so how can you control being ruled by holomorphic forms? So an important point is that a ruled variety Z cross P1 satisfies the following: is that global sections of I forms on Z cross P1. This is isomorphic. This isn't very good. To global sections of I forms on Z. That is, any form on Z cross P1 is pulled back from Z. Okay. And so the point is that in our sort of cyclic cover setting, we can arrange by choosing appropriate degrees that the sections, so the global sections of determinants, the determinant of K, which was this line bundle that we had, inside the global sections of wedge n-1 of Z, or maybe I want this to be wedge n-1 of Z cross P1, or X, sorry. Actually, I think it's Y. What a disaster. Okay. Okay, so we can arrange that these global sections are not constant on any curve inside of Y. Let me change my x's to y's quickly. Okay, so the sort of picture that we have here is if you have any I form on Z cross P1, then it's necessarily pulled back from Z, which means that if it vanishes at one point on one of these P1 fibers, then it has to vanish on the entire fiber. And then suppose this was birational to your X or your Y. Okay, so suppose it's birational to the Y. The point is that you can always find a holomorphic form that's going to vanish at one point of some curve, but it's not going to vanish globally on the entire curve for any curve inside your Y. So this is some positivity property of the determinant, right? It's roughly saying something like the determinant of K is very ample. It's not quite very ample in this case, but it's similar to saying that it's very ample. And so using this positivity property, you can say that there's no way Y can be ruled. So this implies Y is not ruled. Okay. So I guess maybe specifically what Kollár proves is that if you have a line bundle inside of the I forms of a ruled variety, then the line bundle can't be ample or even big enough. Sorry, it can't be semi-ample or something. Ample, yeah, let me just say ample, sorry. Okay, so this is how you use these forms to obstruct the ruledness on the central fiber, and this is sort of the global nature of the argument. What's my time? Okay, but there's a lot of interesting problems that you can ask about besides ruledness. So there's, I guess, a general problem in algebraic geometry to understand the difference between birational geometry of projective space and birational geometry of some random Fano varieties. And I think one of the reasons this problem is so difficult is that in low dimensions, any Fano variety is rational. So it is a bit difficult to get your hands on, well, maybe it's not difficult to get your hands on a non-rational variety, but you don't get to know them until dimension at least 3, which is difficult. So, and one of the main issues is that most straight forward birational invariants agree for Fano varieties. And projective space. So for example, HQ0 is a birational invariant and it vanishes for Fano varieties in projective space. So there's a lot of ways we can sort of compare and contrast the geometries, the birational geometry of rational varieties or projective space with a random Fano variety. Sort of the most straightforward problem is you can ask which Fano varieties are rational. This is the rationality problem. So there's some pretty straightforward conjecture. Any smooth hypersurface X inside Pn plus 1 C with degree at least 4 is not rational. right, so it's expected that a lot of even Fano hypersurfaces are not rational, but this is a very hard conjecture, and there's been a lot of progress in recent years by especially Stefan Schreider, but anyways, in this full generality, this conjecture is wide open, I think. So another way you can compare the birational geometry is you can ask sort of about birational rigidity. So you can ask, when is the group of birational automorphisms finite? So this is known for hypersurfaces, sort of index one phonos. And you should say n is at least 3. Okay. Right, so this is saying that, of course, projective space has many automorphisms, but for a general Fano variety, maybe you would expect that the only birational automorphism is trivial. Yeah, and then somehow it seems that the only this fact is only known for index one phonos. So I think this is an interesting problem. Okay, so another thing we can ask about is the irrationality problem. So can we measure sort of how far a Fano variety is from being rational? The stable rationality problem says for X Fano, when is X cross Pn rational? And the unirationality problem says, so recall something is unirational if it can be rationally parameterized by a projective space. And so this is finite dominant. So there exists a finite dominant rational parameterization. So can the unirationality problem as it stands is, can you give any example of a Fano variety or rationally connected variety that is not unirational? So as far as I know, this problem is totally open. And this is sort of a famous open problem in this sort of area. And then the last thing, which is something I'm going to talk about, is you can look at rational endomorphisms of Fano varieties, and you can ask, can you give constraints on rational endomorphisms of Fano varieties? Or maybe better, can you give an example of a Fano variety with the birational automorphism group is equal to the set of rational endomorphisms? Maybe with a finite degree. Sorry, not of degree 0. Okay, so these are all sorts of problems you can ask. And I guess because it's derived seminar, maybe you can, it's, I think, very interesting to ask whether or not you can approach such problems using derived categories. And I think, okay, so of course, there are a lot of interesting conjectures, especially for cubics, concerning the relation between rationality and the nature of the derived category. But for most part, I will not talk about those today. So I think it is certainly interesting to ask, how can you approach these questions through the derived category? But let me just talk about more applications of this sort of degeneration to characteristic P and the existence of these forms. Okay, so the second application I want to talk about is you have is to the stable rationality problem. So you have X, a degree D hypersurface inside Pn plus 1. And let's say this is very general of degree D. So if D is at least 2/3 n, then XD is stably rational. Stably is not stably rational. All right, so this is also done by degeneration characteristic P. It is interesting to note that this bound is slightly better than Kollár's bound, but this is about stable rationality. And this is about stable rationality rather than just rationality. Kollár's bound is actually for ruledness, which is orthogonal to stable rationality. It's not clear what the relation is, but this is some slight improvement on the rationality problem. So anyways, this is also done via some specialization technique. So what Totaro uses sort of a technique pioneered by Kollár, Talen, and Fazan. And they show that the decomposition of diagonal specializes well. Oops. Admitting a decomposition of diagonal inside the nth Chow group of X squared, this specializes well. And so you also need to understand, so if you have this decomposition of diagonal, you need to know, so why is this constrained by the existence of holomorphic forms? And so the idea is pretty straightforward, is that if you can pull back along the diagonal correspondence. So you have this, the diagonal inside X cross X. If you pull back along this correspondence, you're just going to get the identity on holomorphic forms. But if you admit, so this gives the identity on Q forms. But if you admit a decomposition of diagonal, this means actually, this would imply that every form has to vanish. And I guess that's the point. So a decomposition of diagonal then implies that every form, basically it's supported on something smaller dimension, so it has to vanish. Okay. So this is sort of an application to the stable rationality problem. Okay, let me not spend too much time on this though, because I would like to talk about some of my own work. So I wanted to talk a bit about the irrationality problem. So the irrationality problem is posed as follows. Can we measure how far a Fano variety is from being rational? So this is a bit open-ended. There's a lot of ways to answer this. Specifically, there's a lot of invariants that could measure how far it is from being rational. I am most interested in the degree of irrationality of a variety X. Which is defined to be the minimal degree of a rational map from X to projective space. Okay. So maybe a few quick remarks is that X is rational if and only if the degree of irrationality of X is 1. Okay, so it does sort of measure not whether or not it's rational. And so what we're saying is that if the degree of rationality is larger, then it's sort of further away from being rational. And if the dimension of X is 1, then the degree of irrationality of X coincides with the digonality of X, which is a very useful invariant in dimension 1. So, for example, if the dimension of X is 1 and the degree of irrationality is 2, then that means that X is hyperelliptic. Okay. Okay, so let me mention the result in characteristic 0 for general type varieties. So this is due to Bastianelli, Dupuy, Einlash, Feldman, Ullery. They proved that if X inside Pn plus 1 is very general of degree at least 2n plus 1, then the degree of irrationality is equal to d minus 1. So it's easy to see that the degree of irrationality is at most d minus 1, because if you take any point on your hypersurface, you can always project away from that point, and the degree of that map gets cut down by 1 because the point was on the hypersurface. Another remark to make is that this is outside of the Fano range. And it is very important that it's outside the Fano range, especially for the argument, because the argument heavily uses the positivity of omega x. Which is bad if you want to study Fano varieties, but it's, I guess, good if you want to study Fano varieties using holomorphic forms, which is sort of the premise. Okay, so a typical, so the one way you can see how the positivity is used is if omega x separates q points on X, then the degree of irrationality of X is at least Q plus 1. Okay, so what do I mean by separates Q points? What it means is that for any collection of Q points in X, you can always find a canonical divisor which vanishes on all but one of them. So this is what I mean by separates Q points. So this results in characteristic 0, I'm sorry, not in dimension 1. This result is sort of geometric Riemann rock. So in dimension 1, this sort of follows from geometric Riemann rock. But anyways, this property of separating Q points on X, I would say this is sort of an effective type of positivity of the line bundle omega X. So if you separate more points, then omega is more positive. And so this is the type of positivity that you don't have access to when you're studying Fano varieties, unless you're looking in characteristic P. Okay. All right, so let me mention the first result from this talk, or my first result. So this is joint work with Nathan Chen. The degree of irrationality of Fano hypersurfaces can be arbitrarily large. So maybe more precisely, if xd inside Pn plus 1 is very general, and d is at least n plus 1 minus square root n plus 1 over 4, then the degree of irrationality of x is at least root n plus, this should be a 2 for what it's worth, is at least root n plus 2 over 4. And I guess it's worth mentioning that this gives the first example of Fano's with degree of irrationality at least 4. And I think another thing worth noting is that, so, okay, people hadn't been studying the degree of irrationality maybe that long, especially in higher dimensions, but I don't know of any other technique for controlling the degree of irrationality of Fano varieties. So that, I think that's a very interesting problem to think about. Okay, but in sort of understanding how this argument works, so we wanted to generate a characteristic P, so we first want to start out by using some specialization property, or some property that specializes well and which will control the degree of rationality. So in this case, the specialization property that specializes well is the minimal degree of a rational map to a ruled variety, specializes well. So this is sort of the property we use. And then the claim is also we can control this, the degree of these minimal maps using the positive forms. So let's say, see what the relation to forms is. Let me just write this quickly. So suppose there exists a line bundle L inside wedge I of omega x, such that L separates 2q plus 1 points. Then any separable map from X to a ruled variety satisfies the degree of phi. This is a 2q, not a. The degree of phi is at least q plus 1. Okay, and maybe I have some time to mention how this works. So the idea is that there is a trace map so you can, if you have this finite rational map, you can trace forms. So wedge I omega x maps to global sections of wedge I omega z cross p1, which is isomorphic to global sections of wedge I omega z by what we mentioned earlier. See what happens. Okay. Okay, and then the point is that if you have this positivity property, then and you look at one of these rulings over here. So the rulings are in bright blue, and you look at its preimage, and if you take any 2 points in the ruling, you can find a form up here. Use a different color. you can find a form upstairs that vanishes on every point in the preimage except for so this is this assumption that it separates 2q plus 1 points. And to trace this form sort of by the geometric nature of the trace of this form is going to be something which vanishes at one point in a P1 and doesn't vanish on the other, which is going to sort of contradict this isomer. Okay. So this is how you can use positivity of forms in characteristic P to obstruct low degree maps to ruled varieties. And this is the sort of nature of the argument.
How do you define the trace map without resolution of singularities?
Yeah, so it's a bit annoying. So yeah, I think I don't remember off the top of my head, except it seems likely that we use that X is smooth, but I might not. So even though you don't have a resolution of the general graph of any rational map, still if X is smooth, then if you look at this graph, then you'll be able to pull back I-forms to I-forms on the graph, which is a priori singular, which you might not know how to resolve. And then you want to trace over this map. Yeah, it's a good question. I think what I need here maybe is a double dual. And then I guess once you put a double dual, and then maybe you're only trying to do it away from codimension 1 or something, away from dimension 2. But this sort of the same argument still works. Yeah, good questions. Okay, so I have about 2 more minutes. Okay, so maybe I just want to mention some work in progress with Nathan Chen. So anyway, just because I would like to get it out there. So for a variety X, you can look at the set of rational endomorphisms of X, which let's say is the set of morphisms from X to X, where the degree is at least 1. So it's very natural to ask when the rational endomorphisms X is equal to the birational automorphisms of X. And this is I think this is something that hasn't been studied so much in low dimensions. So one thing is, for complex varieties, when you have, so if you admit some non-automorphism, so some higher degree endomorphism, then that means that your variety is either negative Kollár dimension or Kollár dimension 0. So in some sense, there's not so many examples in low dimensions. There's K3 surfaces, abelian surfaces, and sort of quotients of those, and ruled and rational varieties. And I guess, so it is very interesting to study rational endomorphisms in the Calabi-Yau range, but at least in the Fano range, all these things are rational. And so it's still very interesting to study it, but when you study it, there's no reason not to be studying the rational endomorphisms of projective space, which is sort of very different than studying the rational endomorphisms of the generic Fano variety in high dimensions. So I just wanted to state, so our theorem, and maybe I can talk more with people who are interested, is that if you have a very general hypersurface of degree D, then this degeneration mod P imposes certain congruence conditions on the degrees of rational endomorphisms. And so specifically it says any rational endomorphism congruent to 0 should have degree which is congruent to 0 or 1 mod p for a certain set of primes. Anyway, so I think this is where I want to end. Thank you for your time.
Thanks, David. Are there questions for David?
So can I ask for the last thing, right? So for this rational endomorphisms, so even for K3 surfaces, this is not very well understood, is right? So for example, your result, does it say anything about quartics in P3?
So okay, I think the first result is dimension. The first interesting case is maybe in dimension 11 or something.
Oh, okay.
So it's a bit far from maybe what we want to consider. Like I don't know anyone that's 11-dimensional varieties yet, but yeah, and you can get some results for Kollár as well, but so one thing to point out maybe is that there's this technical issue of these varieties having mild singularities, in particular that the resolutions in characteristic P, when you solve them, that the forms extend. This is only true if the dimension is at least 3. So for surfaces, you don't sort of pick up these forms. But yeah, anyways, other questions?
Can I ask another one? So you there this criteria of how to show non-ruledness, right? So not divisibility by P1, but are there some more subtle things for, let's say, non-divisibility by P2 or something like this?
Yeah, this is. It seems like you could make some sort of argument using forms. But yeah, I don't know. Yeah, that's an interesting question for sure. And I really don't yet know the answer.
Can I ask something?
Hello.
So yeah, you exhibit sort of an infinite family of hypersurfaces where the degree of irrationality explodes, right?
Yeah.
Or sort of, okay, so I just wanted to know, how does it compare with the degree? Is it sort of a square root of the degree growing, or is linear, or is
yeah, so so one issue is that the dimension is going up.
But you don't know if this is sort of sharp for a family.
So I guess the expectation is certainly that these bounds are weak. And so maybe the expectation is that the degree of rationality is roughly D.
Okay.
And my bounds, I don't know.
Actually, David, while you're at it, could you potentially just swing back to the slide where you wrote down the Ein-Lazarsfeld-Ullery result and just sort of compare briefly? Okay, I see. So
yeah,
I see.
so let me see. So I think I forget.
You essentially expect sort of a linear
Right,
function.
so the expectation is definitely linear. I think this is like a square root bound, I think, but it's only in for a certain Fano range. as well.
I see.
Right.
I see. Thank you.
Yeah. So the expectation is that these bounds are quite weak, but then the challenge is to find some other method. On the other hand, the challenge is to find any other method that can control the degree of irrationality. So, especially in the Fano variety case. So, I mean, some natural things to look at, for example, are if you have some conic bundles, can you ever control the degree of rationality of conic bundles? Maybe that's impossible, but maybe that's always 2 or something. But I mean, anyways, there's a lot of techniques that are used to study rationality of Fano varieties, which somehow don't carry over to this degree of rationality stuff up till now. And so the question is, what can be done, I guess.
Can I ask one more thing? So,
yeah.
So is it, have you, okay, this is a vague question with a lot of ignorance behind it, but have you looked at this motivic, sort of this motivic measures technique that was done by you know, Nikkei and then Otem, and where they actually, if I remember correctly, right, there is sort of a motivic invariant that if it is something, then the variety has to be sort of stably rational or something like that. I mean, I don't know, this is sort of another group of techniques, and I wonder if they apply here for the degree of irrationality. Yeah, exactly. Thank you for the references. Yeah.
Yeah, so I think so this is Nikkei and Schinder, and so they showed that a stable rationality sort of specializes in smooth families, and then Kontsevich and Chinkel showed that rationality also specializes well in smooth families, and they use these sort of methods in the Grothendieck group and the Burnside ring to show the specializations. And till now, I don't know any way to generalize this to sort of existence of rational maps. That's very interesting. That's a very interesting question. I think it feels like it's worth mentioning. I think last summer I was in a talk by Eugene Schinder, and he automorphisms and understanding automorphisms using the Grothendieck group. So anyways, there's some sort of attempt to understand rational automorphisms, and sort of how far is that from being able to study endomorphisms or maps between things is a good question. But yeah, I don't really have an answer.
Can I ask another thing? So you see, you study this problem, maps from X to Pn, right, and degree of this. But if we reverse the error and do from Pn to X, right, so degree of unirationality, is it completely like, so the techniques are completely different for the two problems, or there's something in common for them?
So in fact, Kollar's results, so they say, so I guess the difference is that when you're mapping to Pn, you would try and trace forms, and then when you have a map from Pn to X, then you would pull back forms. So Kollar's results actually give results about the degrees of unirational parameterizations. In fact, you can give bounds for the degree of uni rulings of your variety. But having said that, I guess there's still some expectation out there that there should be some Fano variety which is not unirational, and nobody knows how to show that.
But it's not clear whether unirationality specializes, right? So. Oh
yeah, that's certainly. Mm-hmm. But uniruledness specializes.
Oh, okay.
And you can sort of you can specialize this degree, or the divisibility in a ruling sort of specializes fairly well.
Thank you.
Are there other questions? If not, maybe we should thank David again. And there's